Okay, so today we'll be solving for the moment of inertia of a long, thin rod rotating about its end, and we'll define this end to be the pivot point. Alright, so we'll say that is the pivot. OT, pivot. Alright, so we'll say that this rod is of length L, so the distance from here to here is L. So we'll say that this is the origin because it's the pivot point. We'll say this is 0 meters, right? And we'll say that this rod is of mass m. The total mass of this is capital M, okay? Now, we know that since we have to find the moment of inertia, the inertia of any set of objects is equal to the collective, as in summation, of every single mass times the square of that mass from the pivot point, or rather, like the radius. So if we were to have a pivot point of here, and we had a couple masses here, it would be the mass times its radius from here, plus this mass times its radius from here, right? Now, since we know that that is the general equation of moment of inertia, we can solve for a continuous equation because this isn't a collection of different masses, it's one homogeneous mass across the entire long thin rod. We have to use the calculus definition of moment of inertia, which is I is equal to the integral of the radius squared times every small unit of mass, so dm, right? Now, since we're trying to solve for the specific moment of inertia of this long, thin rod, we have to redefine this integral in terms of x, right? In terms of the distance, right? So we have to find how every section of mass relates to its respective section of distance, right? So we have to find the relationship between mass and distance, so dx in this case, right? Because we need to have it in terms of dx to solve for this integral. So how do we do that? Well, we know that if we were to chop this rod up into many little pieces, we'd have a proportional amount of mass for every amount of length, right? For example, if we were to cut this in half, right? Since this is 1/2 of the overall length, then it would be 1/2 of the overall mass, right? So since the length is L over 2, the mass would also be M over 2, right? In other words, the mass of this is M over the length of it, right? Because this is half the length of it, so it's mass divided by 2, right? So if we were to have the overall rod divided up into several little sections, right? So everything was divided into infinitesimally small sections, then what you'd have is each section, each little tiny unit of mass, right, would be of the mass m over its length, right? Now, since this is a long, thin rod, we don't have to worry about the y direction, so we're just worrying about the x. So its mass would be just its total mass, the mass of the overall rod, divided by its length, right? So we know that the relationship between dm and dx is dm is equal to m over L dx, right? In other words, this is every small change in mass is equal to every small change in x times m over L. Which means that if you have a really small amount of length, you will also have a really small amount of mass, right? Makes sense. Now, since we know that this is the relationship, we can plug dm into the integral so that we can solve for it in terms of x, right? So here's how we do that. All we do is, let's just clean this up a little bit so that it's not in the way. Now, what we do is we set I is equal to the integral of x squared, same as before, and then we plug this in for dm. So it would be m over L dx. Now, since when we're dealing with integrals, each infinitesimally small section of this rod is of equal size, we know that since they're all of the equal size, they must all be of the equal mass. So for example, since we divided this into 4 sections, each mass of each section would always be m over 4, right? Similarly, if we had an infinite number of sections, we would have each section be of the mass m divided by the length of the section, right? So, it would be the integral of x squared m over L dx, but since each section is the same, the ratio m to L must be the same. Therefore, m over L is a constant, right? And as we all know, constants can be factored out of the integral. So this is the same as m over L times the integral of x squared dx, right? Now, this is a fairly simple integral to solve from a calculus standpoint, so all you'd have to do is m over L times the antiderivative of x squared dx solved for the length 0 to L, right? So it would be 0 to L of that. The antiderivative of x squared is x cubed over 3, and we're solving for this over the duration 0 to L. So what we would do is this is equal to m over L times, we plug each of these in, so L cubed over 3 minus, and then we plug in the 0, so 0 cubed over 3, which is equal to, well, we know this is a 0, so this just cancels out, we don't have to worry about that. Then it's m times L cubed, which is ml cubed, over L times 3. We can just cancel this out, so L cubed over L is just L squared, right? So this is mL squared over 3. Alright, so that would mean that the moment of inertia for any long thin rod rotating about its pivot point at one end would be mL squared over 3, as in the mass of the total rod, divided by the length of the total rod over 3, or in other words, 1/3 mL squared.